Hello and welcome to today's webinar. I'm Dennis Helsel. Today's webinar is correlation and regression for data with Nondetects. Statisticians call these data censored data. Censored data means that you don't have a unique value, a single number for some observation, but you do know that it is less than or greater than a threshold. And the thresholds that we deal with are either detection or quantitation or in some form a reporting limit back from the laboratory. And so we're going to talk about how to do correlation and regression today without substituting a number in for those Nondetects. What we're trying to cover today is to first demonstrate how correlation coefficients and regression models can be computed without substituting a value like 1/2 the detection limit for your Nondetects. And then second, to motivate you to use these methods because they are available in many different software packages. And so I want to increase your understanding and your trust in them and how they work. And then finally, some of the things that we're doing here are made easier with some of the material in our online course, Nondetects and Data Analysis, and that is available for you to subscribe to. You get a year subscription to it, and that is at our training site, practicalstats.teachable.com. So what are we doing? We're going to be talking about what methods are available to do correlation and regression with Nondetects, why you should not substitute 1/2 the detection limit or 1/√2 or any of the other popular proportions of the detection or reporting limits, and then run the usual regression or correlation with them. You will get terrible results doing that. And I'll show you why. We want to talk about one of the primary methods for doing this kind of work without substitution, and that's called maximum likelihood. These are parametric methods, so they would give you correlation coefficients somewhat similar to Pearson's R, the R correlation coefficient, and similar to standard regression. And so we'll look at different types of correlation coefficients you can do for censored data with an example of those. We'll look at regression with one X variable with an example of that, and then do a multiple regression for censored data with an example of that as well. So that's where we're headed, and then I'll take questions at the end. So the first thing you want to do with any analysis is to plot the data first. This is a data set that comes with the NADA package, NADA package in R. It's also used in the textbook that I wrote on this topic in 2012 that you may be familiar with. If not, send me an email and I will certainly tell you the name and all of the information about that book. Anyway, this is the golden data, and it is lead in various parts of herons. And the idea was to measure it in feathers and to see if feathers would be a good indication of lead and other trace elements in blood and other organs. So I've used the data for the kidney lead levels and the blood lead levels. And we'll see if those are correlated with each other. You can do that with a command that's in the NADA package called senxyplot, and the format is up here. And the format is the X variable, and then the censoring indicator for the X variable, and then the blood data and the blood censoring indicator. And then if you want to put in better labels on the plot than what is by default, which I think will just be the name kidney and blood, the name of the variable that you've got. If you'd like to be more specific, and you could say that this is in micrograms per liter or whatever units, etc., you can put those labels in with quotes. What we're really interested in is, are these two variables correlated? We have 55% of the lead concentrations in blood are censored. They're below 0.02 micrograms per liter. And I believe that the kidney data here are not censored. So we'd like to know, what can I do as far as correlation, and what can I do in terms of a regression equation between these two variables? But this is how you would plot the data. For all of these procedures, The column that says kidney here would be the concentrations of lead in kidneys. And if there were Nondetects there also, then there would be the value for the detection limit in that column. And then on the indicator column, which is the second column right after that, it would have a 0 or a 1, or it could be a true or false in capitals. And these would tell us whether the data are censored or not. So if the value in this column for kidney sen says true, or it says 1, that's an indicating that the kidney value over here is a detection limit. If the value in kidney sen is false or 0, then it's an indicator that it's not censored and that this kidney value is actually a measured detected value for lead concentrations in kidneys. So that's the format. The blood format is the same thing. So if you are familiar, and I'm assuming you are, with the standard methods without censoring, you're interested in Pearson's R correlation. There's something called the likelihood ratio R or likelihood R, and some variations of that can handle censored data with Nondetects without substitution. Kendall's tau is a non-parametric correlation coefficient, if you're familiar with that, and the various trend analysis methods that are used for that. There's a censored version of it. There are a couple, but one is Kendall's tau B, which does compensate somewhat for data that are tied. And as we'll see in an example, when you have Nondetects, you're going to have a lot of ties. For linear regression, the standard regression, whether it's one X variable or multiple regression with multiple X variables, there is a regression using maximum likelihood estimation. That's what the words are behind this acronym MLE. The maximum likelihood estimation version of regression that will handle censored data even at multiple detection limits, and will give you back intercepts and slopes and tests for whether those X variables should be in the model. There is a non-parametric line called the Thiel-Sen line. That's one of its names, and it's the most common one these days. If you've ever done the Mann-Kendall test for trend, this is the line that goes along with that Mann-Kendall test. And there's a censored version called the Akritis Thiel-Sen line that handles Nondetects as well at multiple detection limits. So why not substitute? On the left-hand side are some data. It's a fairly straight line. It should have a fairly high correlation coefficient. I forget what that correlation coefficient is, but it's something like 0.7, 0.8. It's fairly high. And then suppose the data, instead of this, had gotten censored with a number of less than 3s and some less than 1s. And if we put in 1/2 the detection limit, then that would look like the data on the right-hand side, with the open circles being at 1.5 for all the less than 3s and at 0.5 for all the less than 1s. So the main thing is that when you do substitution, you're not just doing that for one number, but multiple numbers, and that produces some sort of a pattern in the data. And that pattern in the data, when you have those, the software doesn't know that that's something that you've made up and put in there. And so it thinks that those are values that you've actually measured and that that pattern is valid. In the case of regression and correlation, that pattern is unfortunately a flat line, or maybe multiple flat lines with a 0 slope and 0 correlation. And so what you're doing is watering down the signal by doing substitution. You're going to be creating slopes for the data on the right-hand side that are lower than they should be, closer to 0 than they should be, because you've blended in a lot of 0 slope data and a lot of 0 correlation data. It also decreases usually the standard deviation or variance of the data, and particularly of the regression line itself, which is called the standard error. It's the standard deviation of the residuals. And so when that is too low, it will tend to bring in X variables, because that standard error is on the denominator of the tests, the t-tests, that you would use to say, should I bring this variable into the model or not? So when that number in the denominator is too low, it's going to make the t-statistic too high, too significant, and it's going to bring in variables that really should not be in the regression equation. So this was all described very well in a paper by Thompson and Nelson in Environmental Science and Technology in 2003. And they mentioned these two basic issues at the end, that you have biased low parameter estimates, mainly the slope, but also the estimate of the standard error. And because of that small standard error, the explanatory variables that should not be in the regression appear to be significant and so are brought in. And so those are the two things that you want to avoid, and you can avoid them by doing the maximum likelihood approaches that we're going to do today. All right, so what is maximum likelihood estimation? Basically, it starts with the observed data. And given that observed data, what values for parameters, slope and intercept, are most likely to have produced those data? And so what does it look at when it's looking at the data? It looks like two types of information. First, the values for the detected observations, just as you would always do, the values for lead in micrograms per liter that you have, and then the observed proportion of data below each detection limit. And for regression and correlation, it's looking at how is that proportion below one or more detection limits changing as X increases. If the proportion of non-detects, which are the low values, decrease, if you don't have many of them with the upper levels of X, that's evidence for a positive slope. If the proportion of non-detects increase as X increases, that's evidence that the data are going down and that you'd have a negative slope. And so those proportions and how they change are the second piece of information that is used without substituting in a number for those. These maximum likelihood methods are parametric, meaning that you have to assume a distribution. The distribution, like with ordinary regression, is the assumption about the residuals, that the residuals have to follow a specific distribution, and generally that's a normal distribution for regression. If the residuals especially are skewed and don't appear to have come from a normal distribution, and we want to check that. If they don't come from a normal distribution, then we would do something like transform the Y variable to get them on a different scale. Common transformation is to take logarithms for data that are skewed and have outliers up at the upper end. So we'll do all of that. This distribution of the residuals is important. And so here's a very poor drawing of these colored areas are the density, like a density plot. It's like coming out at you. And so it'd be like a histogram type of thing. And so starting at the low end, you're increasing so that up around where the regression line is, you've got more data than the other places, and then that kind of tails off again. But you see it goes up higher than it went down lower. So that's skewness, when you have data further away from the regression line on the upper side than the lower side. That's skewness of residuals. The increasing size here represents the increasing variance. It's going out further above and below than it did at the low X values. So that's an increasing variance in the data. You can see that just with the circles, that these four values out here are much more scattered than the data are down at the low end. So with skewness and increasing variance, that would prompt you, hopefully, to take a transformation of the Y variable, something like a square root, a cube root, a logarithm, that sort of thing. If your data do meet the assumptions for regression, then what you would see would be something like this if you plotted just histogram of the residuals. So the 0 line here represents the regression line. The residuals are negative below the line and positive above the line. And you should be able to do a decent job of fitting a nice bell-shaped curve if the data follow a normal distribution. So those are the kinds of things we want to check. Maximum likelihood will fit that curve to those residuals for you. Looking at the data themselves as a histogram, Here's just an illustration with one detection limit at 0.02. I believe that's the golden data. And there are 55% of the observations less than that. What MLE is doing in fitting data, think of it as a slice at one point in X, fitting a curve to the data. It would try to match the histogram values, and that curve would hit near the middle in the top of the histogram. It does that further up around 0.10. And then also it's going to be modifying that curve, moving it back and forth and changing its standard deviation, changing its width in order to get about the same amount of data below 0.02, even though we don't have values for them, so that the area under the curve should be close to 55%. And apparently in this case, the best fit MLE solution had about 52% below 0.02. So those are the pieces of information that are used to come up with a slope and an intercept and a measure of error, standard error, by maximum likelihood that can be used for regression. All right, the way we would usually take a look at this is to look at a QQ plot or a probability plot of the residuals. So this is a probability plot where we've taken the logs of the blood lead concentrations. And so with the data in log units, this looks like a pretty nice straight line. The circles here are the points, the residuals for detected observations. We don't have points here for the non-detects because we don't have the unique number that would be needed to plot them. But what we do have is the proportion of them. So we know that there were 55%. That goes up to about a value of 0 on quantiles of a normal distribution. The mean and median are at 0. And so the lower half of the data are mostly non-detects. And so they would be in here, and their positions, the proportion of them, spaces out the positions for the detected observations. So that's how they affect the QQ plot. So this is not just a QQ plot for plotting the original data after you've thrown away the non-detects. That was discussed in an earlier webinar. You're welcome to go on to our training site and view any of the free webinars on non-detects. I believe there are 5 already there. This will be the 6th one. But this is taking into account the positions of the non-detects, what their percentiles are. There's also a test, the Shapiro-Francia test, which is very close to an R² for this plot. And you can see that's fairly high. If it were 1 exactly, this would say this is a perfect fit to this distribution, which is a log normal distribution. 0.94 is pretty close to that. This p-value is saying the null hypothesis is it fits this distribution nicely, and then we have no reason to reject that. Therefore, we would say taking the logs of the blood lead data is a pretty good set of units to work in doing regression and correlation. And the Pearson's R, or censored version of that likelihood R, does require this normality assumption, as does regression for the residuals. Okay, mathematically, how does it work? I'm not going to go into the math too much, but just a little bit. There's this thing called the likelihood function, and it's just a function that says, how close does my prediction, which would be for regression, the intercept plus the slope times the x variable or variables. These j's could be more than 1, so we could have 3 or 4 x variables. When I get those by guessing on the intercept and slope to start with, and then do a prediction, how close is that to the observed y? So it's going to look at the match between those two. And then it's going to take a measure of their difference, which is usually just the observed value minus this prediction, and pull those all together for all of the n observations to get a total value for L. And then try to change the intercept and slopes so that we can improve on that, and we could lower L. And what's actually going to be lowered is the log. This is the natural log, the log of L, and finding its first derivative, which would give you that inflection point. That would be the maximum. So we want to find the maximum. These are going to be negative numbers. So the maximum up as close to 0 as I can get for this function, this log likelihood. And that would be the best estimates of intercept and slope. So that's how maximum likelihood works. This is the equation for doing regression by maximum likelihood. And I just want to draw your attention to two things, basically. First, the numerator of this fraction on both sides is just a simple subtraction. Y sub I is the observed observation, the ith observation for the value of y. Xi times beta j is the slopes version, the effect of the x's version here of the prediction. And so this is a measure of how close we come to predicting the value of y. This would be the section in here, this first section, for the detected values. On the other side here, on the right side, we've got xi beta j again. So this the slope times the x value for our x variables, and then how close that is to the detection limit of y. So that's the matching part of this. The other thing is this squiggly delta up here, or 1 minus delta. So that's an indicator. That's what's in that second column when you put it in there in the regression or the correlation. And so there's a 0 for detected values and a 1 for non-detects. So let's suppose you had a detected value. So delta I is 0. If you do, 1 minus delta is 1. And we're going to be using this piece of the equation. Raising this piece to 0 just turns it into a 1 over here, drops this part out. So for detected values, this is the piece that's used to compute L and then log L. When it's a non-detect, 1 minus 1 is 0, and the detected part drops out. 0 over here means it's going to be using the second part, which is the CDF, or the set of percentiles. It's trying to say how close can we predict the right percentile for that detection limit. Over on this side, this is the PDF, the probability distribution function that's like the histogram. And we're just saying how well can we, with this piece, predict the actual value? How well can we predict that value for y? So the lack of a match means that this L is an error, and we're going to try to find the maximum log L that will give us the best estimates of intercept and slope that give us the best match. So that's how maximum likelihood works, and that's why it gets around. It does not use any substituted values for non-detects. All right, so we can do parametric correlation coefficients. There's a number of them. They're a lot like Pearson's are. They're not exactly on the same scale. Generally, they're going to be a little bit less, a little bit lower in value for the same strength of correlation than what you're used to in Pearson's R. So if Pearson's R is 0.8 and that or above, and that's a really strong correlation for you, that's your rule of thumb. That's nothing that comes out of mathematics or statistics, but that's what people often consider strong correlations. Then it might be 0.7 and above for these likelihood-based R values. So they're based on the log likelihood, the log of that L that we just had in the previous slide, or more usually a test. And this test, which we'll see later in regression, is just the difference between a model, G0 here. This is a model with no X variables. And then the G model is the regression model that you have. In this case, it would be one X variable for correlation coefficient. And you want to see how much does that one X variable decrease this measure of error. Okay, so let's look at those. The first one is called the likelihood correlation coefficient, or the likelihood ratio correlation coefficient. It uses this G statistic. Again, this is just the difference between two models, a model with 1x and a model with 0 x's. And it looks at the change in those error characteristics and says, does when I add in an X variable, does that decrease the error? And so this difference would be the amount of error that's decreased because that one X is on the horizontal axis. So how well does one X predict, decrease the error in predicting Y? And when you have no slope, that prediction for Y is just the intercept. So that's what this correlation coefficient is. This one is an older slide. It's not the blood and kidney lead data. Apologize for that, but it's easier to grab it. So this is probably the most commonly reported correlation coefficient. It has one issue, is that at the upper end, it can get up higher than 1. And so that's not, that's not real great for correlation coefficients. So there's been a modification to it. This is called, and I'll come back to that other slide, this is called the rescaled likelihood ratio correlation coefficient, or by the name Nagelkerke of the person that computed it, developed it. And it's just taking that same likelihood ratio correlation coefficient and dividing it by its maximum. And so that will be limited to be between plus and minus 1. This is the one I generally use. It's still lower than Pearson's R for the same strength of correlation, but it's actually closer a bit than the just standard likelihood ratio. So it's, of all of these, and there's at least 3 others that are correlation coefficients based on some sort of maximum likelihood statistic. This is the one that's kind of most similar to Pearson's R and would be the most familiar to you. All right, you can do this in the survival analysis package in R. You can do this with a CenReg command, C-E-N-R-E-G, in the NADA package for R. I've modified it slightly. I think it's better, but this is in the, this command Corr Reg is in the material that comes with our NADA course. And what it will do is give you back these likelihood R statistics without having to compute them in a couple of lines of code. Gives you back this QQ plot for the residuals as well. And this is for the blood lead data. So the rescaled likelihood R correlation coefficient's 0.87, so that sounds like a pretty strong correlation with just this one variable. Here's the log likelihood of the model. Here's the log likelihood with no X variables, so just the intercept. Twice the difference of this is that G statistic that's being used to compute these. So that's the parametric approach for correlation. The non-parametric approach is Kendall's tau. And you probably are familiar with it, but I'll go over it just a bit. It doesn't only measure linear relationships, but all monotonic going in the same direction relationship. So it allows changes in slope. You could have a curve, a continually generally increasing relationship or continually generally decreasing relationship, not up and down. That's not monotonic. But things that are going up and the rate is changing. That will be picked up fine with Kendall's tau. Pearson's R and these likelihood R's are limited to linear relationships. Kendall's tau does not require the normality assumption for residuals, so you don't have to worry about it. If you ran it on the log of Y and ran it on Y, you'd get the same Kendall's tau. It does allow censoring in both the X and Y variables, so that's a big advantage. And it has a regression line, if you want to call it that, associated with it. For one X variable, that's the Akritis-Thiel-Sen line. This is the equation for Kendall's tau A. Usually with censoring, it's actually Kendall's tau B that's used. But the important thing here is that you're looking at the number of concordant pairs of data. So these are pairs of data where as you increase in X, the Y also increases, minus the number of discordant pairs. When you increase X, Y goes down. So that's the statistic that's used. You can do that whether or not data are censored. So here's just a simple example where the X variable is the year. The Y variable is something that's being measured here. And if you compare 20 to a less than 10, that's a decrease, so that gives you a minus. The discordant, it's a discordant. 20 to a less than 10, which is a minus. 20 to a 7 is a minus. 20 to a 3 is a minus. 20 to a less than 3 is a minus. So even though I don't know the numbers for the less than 10 and less than 3, I know that they're decreases. So I put those in. A less than 10 to a 7, that's a 0, because I don't know what that less than 10 is, and it could be higher or lower than 7. Less than 10 to a 3 is a 0. Less than 10 to a less than 3 is a 0. So these do not count for either pluses or minuses. 7 to 3 is a minus. 7 to a less than 3 is a minus. 3 to a less than 3 is a minus. So from these, it looks like there's some indication of a down trend here, going down in y as x increases, time increases. That's how Kendall's tau is computed. So you can get that back in the NADA package with a command called sen_ken. Again, I've modified it and enhanced it a bit, at least I think so, with the ATS command that's in our course. That will give you back the line in a nice format and print it out for you with the intercept and slope. Compute Kendall's tau B. So B is a tie correction version of Kendall's tau. It's still going to be quite a bit lower than Pearson's R. It is still, the ties of all of these non-detects are still affecting Kendall's tau, if you want to think of it that way. So you wouldn't compare Kendall's tau to Pearson's R, and this is 0.4 and Pearson's R was 0.87, or the likelihood R is 0.87, so that this is a worse correlation coefficient. It's just on a different scale. And you can certainly compare this Kendall's tau to another Kendall's tau with a different variable, and if it's lower, then it's not as good of a correlation. If it's higher, then it's a much better correlation. And you get back the test for whether that's significantly different than 0. So all of these things with correlation have been done without putting in any number for the non-detects. So the parametric approach, I would use the rescaled likelihood ratio R, or Nagle-Kirkes. It's only, the only downside of that correlation coefficient is either a long name or a difficult to pronounce human's last name. It works very well. Make sure the residuals follow the assumed normal or log normal distribution, that your XY relationship is linear, and only the Y variable may be censored with this asterisk that just in the last few months, there's been a new R package. I don't have it up here. It starts with the lowercase CLIK, click. And I think it might be click Corr, C-O-R, or C-O-R-R, I forget which. So it's a brand new package that computes the likelihood ratio R, so it would be this one. It's not the one that's rescaled, at least yet, but computes that when both X and Y are censored. But the work on regression is still ongoing in various universities. I believe this click Corr package was developed at the University of Michigan, if I remember correctly. I hope that's right, if anybody's listening from there. So the non-parametric approach is Kendall's tau. Kendall's tau B has some corrections for ties, although they're still affecting it to some extent. It just means that the numbers are going to be lower, but you can use it in exactly the same way. And don't use, for the last thing to remember, don't use substitution. You will get bad answers for Pearson's R after you stick in a half. All right, regression, how do we do that? You can do that with the sen_reg command in the NADA package. This is the one that I've done. I like it better, of course, which gives you back nice estimates of the slope value, the intercept, the p-values for that slope, all without substitution. You'll see these log likelihood models and log likelihoods of the intercept only, telling you this is an MLE. Okay. The sen_Corr Reg, that's the command that I developed, and the sen_reg command in the NADA package assume that you want to take the logs of the Y variable, because anything with non-detects is skewed in essence. So a normal distribution rarely, if ever, works well. And you will get predictions that go negative fairly easily with assuming a normal distribution. So the default is a log normal. It's taking internally the logs of the blood data that you put in here. Gives you back the correlation coefficients, including one extra one, gives you back the regression, and again, the slopes, the intercepts of the formula, and the p-value for whether that slope is equal to 0. This is a very small p-value that's telling you this kidney variable is a significant X variable in a model, and this would give you a better prediction of Y than just the mean of Y. Gives you the formula. I put this on the PowerPoint, but here's the formula down below. The log of blood lead has the intercept and slope, and then you can just transform that and get the simple exponential type, power type equation, which will look like a curve. You can check the assumptions with these QQ plots on the residuals. Again, they're appropriately adjusted for the non-detects. You can plot the results. So this is the plot of the predicted straight line with that intercept and slope on the sen XY plot. Seems like that's a reasonable fit as far as a log of blood versus lead in kidneys. Note that these dashed lines represent the non-detects, and look at the frequency that they occur. There's a lot of non-detects, so a pretty high proportion of non-detects at the low end for kidney. When the lead in kidneys increase, there's above 3 point something, there are none. So all of that is evidence that the concentrations are going up in blood as they go up in kidneys, and that is being used in the MLE along with this pattern for the detected values in order to give you back intercept and slope. You could transform that back out, just take the EXP of it, and you get this nice curve function, and plotting the data in the original Y units of concentration of lead. You could do a non-parametric version of all of this. It's the Accretus Thiel-Sen line. It's the senken command in the NADA package. Again, my ATS command as well does it and gives you back the intercepts and slopes. This is actually a fairly similar intercept and slope because the log of the data looked nice and linear. So though the Kendall's tau does not depend on whether it's linear, once you start to put in a model here, you're using a straight line model, then you're saying, I need to get this in units that make it look like a straight line, and the logs look like a straight line. Just the original blood concentrations, it looks much more like a curve. And so this intercept and slope are actually pretty close to the regression, which tells you that the residuals in the MLE were pretty close to a normal distribution. Anyway, you can plot the ATS line here with the log on the y-axis, and you can retransform it and get the nice curve as well. All that's done in the ATS command for you. How does this ATS get its slope? It's again an iterative process. What it's doing is saying there's a property of the Thiel-Sen line when there is no non-detects, when there is no censoring, that the Thiel-Sen line is the slope that produces a tau equal to 0 on the residuals. It has 0 correlation as measured by Kendall's tau for the residuals versus X. So you can use that to iteratively solve for the slope and the intercept by computing the Kendall's tau of the residuals, and then the slope and intercept that are best are the ones that produce a 0 Kendall's tau versus X. And so that's what's done internally. And so the summary for all of this, we're going to get to multiple regression quickly, is that the parametric approach is maximum likelihood. Only the Y variable can be censored except for this brand new package that's just come out that will do a correlation, but not yet regression when the X is censored as well as Y. Make sure the residuals follow a normal distribution. It must be linear, and it estimates an estimate of the mean of Y given the X's. Whereas in the non-parametric approach, the Akritis-Thiel-Sen line estimates the median of y given one x, and it, at least to date, only works with one x variable. But it has no normality assumption. It does assume, since you're doing a linear model, that the data look like they're linear on the plot. All right, multiple regression. Again, you can do this with the sen reg command in the Nada package, or you can do it with the sen Corr Reg in the course. And this data set has TCE concentrations in groundwater with the concentration here with the detection limit of 1. The TCE sen true means that all of these are less than 1s, the first 6 entries. And the 4 variables were land use, and that had some kind of a number assigned to it, and I don't know what that was anymore. It's an older report. It wasn't a very precise kind of thing. Population density is a little bit better. It was population density for a defined area around the well, the percent industrial land use around the well, and the depth to water for the well. So these are the 4: land use, population density, percent industrial, and depth are the 4 explanatory variables, and we want to see if any of them help you to predict a TCE concentration when some of those, and actually this is about 80%, are below 1. With any kind of multiple regression, multi-collinearity is the most important issue. Are there any relationships among the X variables? And I won't go into that, that you should know that from your standard regression stuff. If you don't, then pick up a new regression book, one that's written in the last 20 years, or take our AES, Applied Environmental Statistics course. Anyway, you can compute that multi-collinearity. You want them to have VIFs all below 10, and so you can just use a VIF command in R. Same command for when you're doing regular multiple regression, and you can get back the VIFs for these 4 variables. They are not correlated with among one another, so they are not violating any of those independence of the X variable assumptions that are important and can result in a bad regression if you don't pay attention to that. So we don't have that. We can come out with a regression model. A multiple regression model gives you back p-values for land use, population density, percent industrial land use, and depth. Also, importantly, gives you back some of these MLE statistics and an AIC, although I don't see it right here. It did come out on the output, but I don't see it here. I must have chopped it off to fit all of this on this slide. So the AIC, which is a measure of quality, and it's a measure of really lack of quality, a measure of error of a regression equation. You want to kind of keep that small, and it's 395.8. So the question is, if I tossed out one of these, could I get the AIC lower than this? I tossed out the percent industrial land use first. So tossed out the percent industrial land use. Here's the 3 variable model with its p-values. Here's the AIC and the printout. 394.3, it's actually lower than it was before. So this 3 variable model has less error than the 4 variable model did. You could compute likelihood R-squareds for both of these. In fact, they are written up here. Like with regular regression, this R-squared is always going to go up when you put in more variables. So this R-squared is 0.1057 for a 3 variable model. And for the 4 variable model, I don't have it on here, it was higher than that. So R-squared is not something that's telling you if it's bigger, it's better in regression or this censored regression. You need something that gives you a penalty for throwing in new variables, more variables. This 3 variable model has less error. It's a better model because its AIC is smaller. 2 variable model, throwing out the land use variable, has a AIC that's even lower, 393.6. And so it is a better model than the 3 variable model. You'll notice that it still keeps population density in with a p-value of very small, and the depth with p-value of 0.06. So this is something that you may read in textbooks. It is that AIC, and there's another statistic called BIC, and there's a couple of others on top of those. They all generally underfit, don't give you quite enough explanatory variables when they're applied to data where you know what the answer is as far as which variables are important. In other words, simulated data. So if you get a variable whose p-value is not far above 0.05, I would tend to keep it in there because that's still evidence. There's nothing magic about a 0.05 cutoff. And BIC is worse at this. So this is the lowest AIC model with this data, 393.5. It's not yet the lowest BIC. If we go down and drop out the one with 0.06 and just have population density in there, the BIC is slightly lower. The AIC is actually quite a bit higher. So in my opinion, AIC is a better statistic than BIC to use for regression modeling because it's not susceptible to underfitting, having too few variables in the model. So the one with the smallest AIC is the one I generally go with, especially if those additional terms that would get thrown out later have still reasonably low p-values. So anything below 0.1, certainly I would keep in the model. So you can do correlation and regression for data without substituting. The methods are available in the survival analysis sections of statistics software. They're in there in all the main statistics packages. So look for survival analysis. You'll have to wade through some of the jargon that is used in survival analysis, and the fact that in medical statistics, which was where it was all developed, they deal more with greater thans than less thans. So you want to look for methods of either left censoring, that's less thans, or interval censoring when you can specify 0 is the low end or something else is the low end and the detection limits at the upper end. That's done for you in the NADA package, and it's done even more in the routines that are in our course, which is also named NADA. So thank you for attending today. I do want to do questions. Just to say before I get to those that the Statistics for Censored Environmental Data using Minitab and R was the book I mentioned earlier. It's the second edition of the book, came out in 2012. And all of the material and more is in our Nondetects and Data Analysis course. And that's pretty much it. So let me take a look at the questions that you've submitted, and I'll answer as many as I can. Can you provide a suggestion or a better test or solution to incorporate ancillary data with y-axis data that have MDLs to do a correlation trend in a proper manner? Well, I think that's what I just did, unless I'm not understanding your ancillary data. You could do tests with regression. You can use the ATS procedure to do the equivalent of the Mann-Kendall test for trend. In our course, we will soon have a version of the seasonal Kendall test for trend. They're using a modified version of that ATS command. And all of those, both MLE and the Kendall-Stau-based procedures handle multiple detection limits. So that works great. Everything that we've seen today handles multiple detection limits. Okay, in the previous webinar, how censored data methods work, which is also going to be the next webinar, you mentioned that using imputed values from survival analysis methods, ROS, and sticking them in other analyses should not be done. So yes, those imputation methods are there to show you they're not data. They're really just holding, they're placeholders that hold the place for that part of the distribution of the data, just like the area with the dashed lines that I showed you earlier for MLE does for MLE methods. They're just filling up that space. So if you put them in, you're assigning them to a specific observation and you don't know what those are. Anything below the same detection limit, you have no idea which number to assign to which value, which observation. So if you rearrange those imputed values, you might get a different result for a t-test, different result for a principal components analysis. There are better ways of doing all of those things. My suggestions are all in the NADA course, but you can do the equivalent of t-tests and analysis of variance, and here we've seen regression. In the course, we talk about multivariate methods, cluster analysis, and that kind of thing for data when you're not imputing a number for it. Okay. Brian, have you considered using censored quantile regression, which allows you to estimate a median and other quantiles without making parametric distributional assumptions? Yes. Yes, I'm a big proponent of quantile regression, not as experienced at it as you are. But yes, I have used that. I've particularly recommended that when people wanted something like a tolerance interval. And so they want to do a 95% interval around a 90th percentile, and they want to do that as a function of x, or maybe x is time, and is that changing? And so doing quantile regression is a great approach, and I've done it myself a number of times. I wish I had put it in the 2012 book. I'm getting close enough to retirement that I don't know I'm going to do a third edition, but if I do a third edition, it will definitely be in the book. So if not, I think that the publications that you've done would be a great resource for people, so I'll just mention them. Find some of the publications on quantile regression by Brian Cade and others, and you will get familiar with it. And it's done very easily in the Corr Reg package in R. How might all of this relate to missing data? Well, it doesn't, for the most part, at all. There are ways of imputing data for missing data that could be done. It's a different thing because with missing data, you don't necessarily know a threshold. So you have less information often with missing data than you do with censored data. That's one of the reasons you should use censored data procedures, is because you do have that threshold and there's a lot of information in that threshold. So you may have as much as 70% of the information in just knowing the threshold, and it's less than 1 than you would if you had the actual individual number at 0.83. So there's a lot of information in that threshold. You want to use it, and we've just talked about methods for using it. And you don't have that always with missing data. So you have to use some other kind of procedures usually. How are the data set up to indicate an MDL? Is there an additional column to indicate detection, non-detect? Well, so what I've done here, one approach is to put in an indicator, 0, 1. And if there's a 1, it's a censored value, and whatever number is in the first column, that censoring indicator's in the second column, whatever number's in the first column is the detection limit, and they don't all have to be the same. So you could have 20 different detection limits, and there'd be 20 different values in the first column, all of which have a 1 in the second column that say it's less than that. However, if you are talking about, I have data that are between a detection limit and a quantitation limit, then you could go to a different format. And the survival package does this in R, and that would be my goal. And I think this is the big failing of the NADA package in R, is it only is set up for having 0 as the low end. And so it's an easy fix. Its coding is never easy, but you would use same number of columns, 2 columns. The first one would be the low end. The second one is the high end. That's called the interval format. And that, I think, is the most flexible format and the most general format. And if you only know it's less than 1, then it would be 0 in the first column and 1 in the second column. If you knew more than that, if you knew that there were 0 to 0.5s for being less than the minimum detection limit, making the statement about detection limit being different than other kinds of limits, 0 to 0.5, so it's truly, I don't know that this is anything different than 0, then you'd have that coded as 0 in the first column and 0.5 in the second column. And then maybe if it was a 0.5 to 2, and so it might be reported to you as a less than 2, but it's 0.5 to 2. It's in that range because it's not below the detection limit. It's below a quantitation limit. Then you could put in with the 2-column format, the indicator format, 0.5 in the first column and 2 in the second column. And it would be between 0.5 and 2. You can do that in the survival package. You cannot do that in the NADA package. I would like to see that changed, but I don't have any authority to change it. All right, thank you. Thank you very much for attending. Goodbye.